Hi guys, today we're looking at the constant acceleration formula. Now you would have done this at GCSE, so it's going to be a bit of a recap, but hopefully there'll be quite a few problems here that are going to be quite challenging to you, so it's not going to be boring at all. You may have heard of this topic, or at least the formula under a different name. Perhaps you recognize the word SUVAT. Okay, so SUVAT formula. There's 5 that we tend to use normally. I'm going to show you 2 of them. I'm going to show you how to derive 2 of them and see if you can derive the others. But before we move on to that, we're going to start by looking at displacement time graphs and velocity time graphs. So you need to be able to not only interpret those type of graphs, but also draw them from a problem, from like a worded problem. Okay, so we're going to start off with that. We're going to go through the SUVAT formula. And like I said, there's 5 of them to look at. And then finally, we're going to look at how we can use those formula to solve different types of problem. Normally, the type of problem would involve gravity. Okay, so vertical motion under gravity. But we also have type of questions where you have car that's accelerating at a constant rate, or a bicycle or something like that. So quite a variety of different questions. And students tend to like this topic because they can relate to it in practice. You know, it's one of those topics where you can actually see how the maths can be used to solve a real life problem. So hopefully you'll enjoy it. Okay, so here's an example of a displacement time graph. Now in the vertical axis we have displacement, and that's measured in meters. And that could be both positive and negative. And in the horizontal axis we have time, and that can only be positive. Okay, we're not going to deal with negative time. So here we have the journey of a person, we'll say, and they start off at home. So t is 0, displacement is 0, and then they travel 2 meters till they get to the point A. That takes them 4 seconds. Now you'll probably notice that we've got just a straight line graph here, so there's no curves at all, and that's because we're just dealing with this. In this question we're just dealing with constant velocities, okay, not changing velocities. So the velocity is actually given by the gradient of the graph. So on this journey from 0 to A, they're traveling 2 meters, okay, so displacement is 2 meters. It takes them 4 seconds. So the gradient of the line would be the change in y over the change in x, or in this case the change in s over the change in t, so 2 over 4, or half a meter per second. So that would be the velocity from 0 to A. Now from A to B, they don't change their displacement, and that's because between A and B the velocity is 0, so they're stationary for 1 second there. Then from B to C, they actually change direction and head back towards the starting point, which they reach at 7 seconds, and then they continue past the starting point until they get to point C, which is 3 meters from their starting point, but in the opposite direction. In this question, we've chosen right to be positive, okay? And we could also work out the velocity from B to C. That's going to be a negative velocity because it's in the opposite direction. And from C to D, guess what's happening there? Yep, there's got a 0 velocity again, so the displacement is constant. And then from D to E, we have another positive velocity. So they head back from their negative displacement of -3 meters back to the starting point, which is a displacement of 0. Okay, so they go backwards and forwards and they end up where they started. Now you can see here the gradient from D to E is much steeper than the gradient from 0 to A, and that's because it's a bigger velocity, a bigger magnitude velocity. So that's the kind of thing that you need to be able to interpret. You know, what's the velocity, when are they stationary, for how long are they stationary in this journey, and things like that. All right, so displacement time graphs I'm not going to spend too much time on because they're fairly straightforward. But just bear in mind, in this question, we just have constant velocities and 0 velocities. Okay, you might want to wonder what it would be like if you had a changing velocity. What would if the journey from 0 to A, if there was an acceleration there, what would that look like? Okay, well, we'll see on the next slide. Just to summarize what we've done, or the key points from that graph, when you have a displacement time graph and you have a horizontal line, that means there's zero velocity. Okay, there's no change in displacement over time, so the velocity is zero. When you have an increasing straight line, then that's a positive velocity. When it's a decreasing straight line, it's a negative velocity, but also constant velocity. Now, if you do have a curve, like I mentioned before, then this is when you have an acceleration. So the velocity is no longer constant. In fact, the velocity is getting bigger and bigger as we increase time. And you get this exponentially increasing curve. Okay, and we'll be dealing with questions that involve constant acceleration when we look at velocity time graphs. So just remember those 3 points, folks, very important. And like I said, you need to be able to interpret the graph from a worded question, be able to draw a displacement time graph, and also a velocity time graph, which we'll do some examples of later. Okay, key things here, you might want to copy these down. Velocity is the rate of change of displacement, so it's the gradient of your displacement time graph, so the change in displacement over the change in time. That's what we mean by the rate of change. It's a change in something over time. The gradient represents velocity. The displacement time graph is always a straight line graph, and when that's the case, the velocity is constant. Average velocity, we haven't mentioned that. The average velocity is the displacement from the starting point over the time taken. So you could actually have an average velocity of 0 if they start and finish at the same point, because the displacement would then be 0. The average speed, on the other hand, is always positive, and that's because we take the total distance, okay? So the distance is always positive, remember, over the time taken. So the average speed will always be positive, but the average velocity could be positive or negative if you end up with a negative displacement. So those two things give you different values from the same question, velocity and speed, okay? Right, let's have a look at an example. In this example, we have a cyclist that rides in a straight line for 20 minutes. She then waits for half an hour, and then she returns back home. So the journey from 0 to A, that's when she's traveling. From A to B, that's where she's stationary. And then from B to C, she returns back home at point C. Now, B to C takes 15 minutes. So this is 65 minutes here when she gets to point C, which is actually back at the start. So we need to work out the average velocity for each stage of the journey. So 3 stages. Let's start off with that. So part A, let's just say the journey from 0 to A. Remember, the average velocity is the displacement over time. So the displacement is actually 5 kilometers. Now, it does say here that we need to put our answers in kilometers per hour. Normally, we'd convert this to meters per second, but they want the answer in kilometers per hour. So they're actually going to make our life easier doing that. So 5 kilometers over, well, 20 minutes. Well, 20 minutes is a third of an hour. So we need to divide by a third to get that gradient. And that's going to give us a gradient of 15 kilometers per hour. Okay, so that's the journey from 0 to A. Let's do the same from A to B. Well, actually, the velocity from A to B, I think you'll know what that is without doing any calculation. It's going to be 0. Yes, because the person's stationary. The cyclist is stationary between A and B, so there's no displacement there, no change in displacement. Now, from B to C, we have another gradient to work out, and that is the change in displacement over the change in time. This time we're looking at 15 minutes. So let's see if we can work out the average velocity there. So again, it's 5 kilometers. It's going to be a negative velocity, okay, because the gradient is negative over time. So 15 minutes, which is actually a quarter of an hour, and we get minus 20 kilometers per hour. Okay, so that was part A there. For part B, it says write down the average velocity for the whole journey. Well, remember, the average velocity is the displacement over time. But the displacement from the starting point is 0, okay? They return back to the starting point at point C. So for part B, it's very easy. So the average velocity is equal to 0. For part C, we need to work out the average speed for the whole journey. Now, average speed is the total distance travelled over the total time. So from 0 to A, the cyclist has travelled 5 kilometres. They then stay at that 5 kilometre displacement until they get to B, and then they return back to the start. So they travel another 5 kilometres to get back to the starting point, which is at point C. So we have a total distance of 10 kilometers. So this is the average speed we're working out here. So a total of 10 kilometers, and that takes 65 minutes. So we need to convert these minutes into time. So 65 minutes into hours, I should say, sorry. Right, so that's 10 divided by 65 and times 60. What that does is it's basically saying I'm going to divide by 65 divided by 60. And that's the same thing as multiplying by 60 over 65. So we get the time in kilometers per hour. And that gives you an average speed of 9.23 kilometers per hour. It seems about right for a cyclist. Yeah. Okay, so there we go. There's our first example. Okay, before we move on to velocity time graphs, here's an opportunity for you to do a little bit of practice on displacement time graphs. Again, if you find this very straightforward, I wouldn't spend too much time doing these questions, but maybe try a few and see how you get on. Compare your answers to the ones in the back of the textbook. And if you feel that you can do some more challenging ones, just try the last couple in the exercise, and then we'll move on. Okay, so you might want to just pause the video, and then we'll come back to it in a minute. Okay, here's an example of a velocity time graph. So in the vertical axis we have velocity instead of displacement, but again we have time in the horizontal axes. Now again, it's a straight line graph because we deal with constant acceleration. Here we have actually changing velocity. So the journey from 0 to A, we have a change from 0 to 3 meters per second. So that means there must be some acceleration there. From A to B, in a velocity time graph, a horizontal line means a constant velocity. So from A to B, the velocity stays constant at 3 meters per second. From B to C, they're still traveling away from the origin, but they're slowing down. The velocity is decreasing, but it's still positive. So all of this journey from 0 to C, they're traveling away from the starting point in the same direction. At point C, they actually have a velocity of 0, so they come to a full stop. Now, from C to D, they are now traveling with a negative velocity, so they're heading back in the opposite direction to the way they started, heading back towards the starting point. After 6 seconds, they have a constant velocity of -3 meters per second. So they get to point E, and then from E to F, they are still traveling to the left. I think we've chosen right to be positive. Yep, so they're still traveling to the left, and when they get to F, their velocity is 0 again. So they travel from 0 to C in one direction. At C, they're stationary. From C to F, they travel in the opposite direction, so heading back toward the starting point. Now, at point F, they may still be some way from the starting point. It doesn't necessarily mean that they're back at the origin again. So we would need to be able to work out the distance travelled in order to determine where they are at point F. So, key points from this graph. Increasing gradient means positive acceleration. Horizontal line means fixed velocity. A decreasing gradient means a negative acceleration. Okay, so still a positive velocity and then a negative velocity, but the acceleration is negative, and then constant velocity and then positive acceleration. So it's the gradient that gives you the acceleration, and 0 velocity when the curve, or the straight line I should say, crosses the x-axis, the horizontal axis. So key points here, the velocity is 0 and the object is stationary. Okay, so here we have a line along the t-axis here. So if velocity is 0, the object is stationary. If the straight line is above the t-axis, then they have a positive constant velocity. Okay, so the velocity is constant and they are still traveling away from the starting point. If you have a positive gradient, then we have a positive acceleration, so they're getting faster and faster. And a negative gradient just means the acceleration is negative, and they will be getting slower and slower. So there's 3 key points from the velocity time graph. Okay, so just to summarize then, acceleration is the rate of change of velocity, so the change in velocity over time. In the velocity time graph, the gradient is the acceleration. If it's a straight line, then the acceleration is constant. Okay, so an increasing gradient as a straight line, or a decreasing gradient, the acceleration is constant during those times. We sometimes refer to negative acceleration as deceleration. So you might have an acceleration of -5, that would be a deceleration of +5. Now, something I've not mentioned, and something that you'll need to be able to work out in problems involving velocity time graphs, and that's the distance travelled, and that's given by the area under the straight line graph. Okay, let me just go back to the previous example. So in this example, the area under the graph between A and C, that represents a distance travelled in one direction. Okay, so to the right, we'll say. So if you worked out that area, that tells you how far the person has travelled to the right. If you then work out the area under the graph, think of that as a negative distance travelled, if you like. So they're travelling in the opposite direction. So in order to work out the total distance travelled, we'd just be adding these 2 areas together. So that tells you how far they've travelled in total. If we wanted the displacement, we'd have to make this area positive, this area negative, and then add them together. And that would give you the displacement. And it looks like from these 2 areas that this bottom one's a bigger area, so their displacement would probably be negative. Okay. So we're going to do a few questions involving displacement, because it can be quite difficult in places. Let's just get you to have a little go at doing that first of all. So for each of these graphs, can you work out the acceleration in each case, the distance travelled from A to B. Okay, so just spend a few moments doing that. So pause the video, have a go, and I'll give you the answers in a moment. Okay, hopefully you didn't find that too challenging. Let's just give you the answers to these. So for the first one, we have a horizontal line. Let's do this in blue. So the acceleration is going to be 0 in this velocity time graph. Okay, so remember the acceleration is the gradient, so acceleration is 0. What about the distance travelled? Well, the area under the graph from A to B, we've got a height of 4, we've got a width of 5, so 4 5s are 20. So that's the distance travelled. The next one, we have to work out what the gradient of this line is to get the acceleration. So that's 8 divided by 5. I'm just going to leave that as a fraction. So that's meters per second squared. The area under the graph, well, imagine we have a right angled triangle here. Let's just draw that. Okay, so we just need this area. So area of a triangle, half base times height. So the distance is going to be a half times 5 times 8, which leads to 20 meters. Okay, I can put meters there as well. Next two, gradient again for the acceleration, positive gradient, so it's going to be a positive acceleration. So the change in y, let's just see if I can do like this for you, over the change in x to get the gradient there. So 6 is the height and 5 is the width. So change in height over the change in width. So 6 over 5 meters per second squared. Distance travelled, this one's, you can do it two ways. You can think of it as a rectangle plus a triangle. Okay, just work out those two areas and add them together. Or you could use, if you remember it, you can use a formula for a trapezium, which is half the sum of the parallel sides, which is the height from 0 to A and 0 to B, multiplied by the width between those two parallel sides, which would be that width of 5 there. I do it both ways really. I think working out the two areas and add them together is a little bit simpler, and that's probably the way I would do it, to be honest. So 1, 2, 3, 4, 5, 6 times 5 is 30, divided by 2 is 15. So that's the height of the triangle, and then the height of, that's the area of the triangle, and then the area of that rectangle on the bottom is just 10. So distance travelled is 25. Okay, hopefully you got that. The last one, this time the gradient is negative, so it's going to be minus 6 over 4, minus 3 over 2 meters per second squared. And the distance travelled, well, distance is always positive, so with the areas being above the t-axis, it's going to have a positive value there, so half base times height gives you 12 meters. It's a little bit more complicated when our velocity time graphs go below the t-axis, because then we will have actually a negative displacement. So I'll show you how to calculate that in a few moments. In example 1, we have the velocity time graph that represents the motion of a cyclist moving along a straight road for a period of 12 seconds. Now for the first 8 seconds, she's moving with a constant speed of 6 meters per second. She then decelerates to rest in a further 4 seconds. In part A, we just need to work out the displacement from the starting point during the 12-second period. Okay, so how far has she travelled? And incidentally, because the graph lies completely above the t-axis, the distance travelled and the displacement are the same. Okay, it's only when the graph lies partly below the t-axis that you'd get a difference between the distance travelled and the displacement. So let's just work out the total area under the graph. That's going to give us our distance travelled and consequently the displacement as well. So we've got a rectangle and a triangle, and we're just going to work out the areas of those two and add them together. Okay, so it's going to be 6 times 8 for the rectangle, and we're going to add on that triangle, so a half times the base, which is 4, times the height, which is 6, and if you add those together you get 60 meters. Okay, so distance travelled or displacement is 60 meters. Now for part B, we need to work out the deceleration of the cyclist. Now I'm going to work out the acceleration first. Acceleration is the gradient of the line, and that's going to be a negative because it's sloping downwards, and it's the y difference, which is 6 over the x difference I should say, which is 4 seconds. So we get an acceleration of minus 1.5. And the reason I've done the acceleration is just to show you the difference between acceleration and deceleration, because sometimes students do miss out the word deceleration and they just work out the acceleration, or they might forget to change the sign. The deceleration is actually positive 1.5, and if you put a negative in the exam you'd have lost a mark there. Okay, so that was that first example. That's pretty straightforward. In example 2, we have another particle moving in a straight line, and the particle accelerates uniformly from rest to a velocity of 8 meters per second in t seconds. Okay, so we need to sketch this. Okay, the particle then travels at a constant velocity of 8 meters per second for 5t seconds. So t is some constant we need to find, and then decelerates uniformly to rest in a further 40 seconds. Right, let's just sketch what's going on in this question. Okay, so I don't think that worked. Let's try that again. Right, so accelerating from rest, and then constant velocity, and then decelerating. There we go. So for part A, it says sketch the velocity time graph to illustrate the motion of the particle. Well, we do need to label this. So we have a velocity of 8, and that's after t seconds. So I'm just going to put a little dash there and put a t there. So that was t seconds. She's accelerated from, the particles are accelerated from rest to 8 meters per second. It then has a constant velocity for 5t seconds. So this length here is 5t. Okay, so that makes this point 6t. And then decelerating in another 40 seconds till the particle comes to rest. So this point here, let's just put a little arrow there, that's going to be 6t plus 40. Okay, so there we go. That's everything that you would need to include on the sketch. Given that the total displacement of the particle is 600 meters, find the value of t. Okay, well, the displacement represents the area under the graph. Now, I think it would be easier to use the formula for trapezium in this case, because we know that side is 5t, the bottom side is 6t plus 40, and the distance between the two sides, the two parallel sides, is 8. So let's just set our displacement equals 2. So it's half the sum of the parallel sides times the distance between them. Okay, let's do half times 8. That gives me 4. Divide 600 by 4. So that takes care of the half and the 8. 5t plus 6t is 11t plus 40. And that's 150. Let's take that 40 over to the left hand side. And that's going to give me 110 on the left. And if we divide by 11, then we get 110 over 11, which is 10. Okay, so the value of t is 10 seconds. And a little bit of practice for you folks. Exercise 9b. Again, any problems, bring them to class and we'll go through them there. Right, so a little bit of a challenge question for you. Here we have the journey of an object travelling in a straight line for a 10-second time interval. And there's a few questions here that you need to work out. Okay, after how long did the object change direction? What's the total distance travelled? What's the displacement from the starting point after 6 and 10 seconds? I'm going to let you guys have a go at this for homework, and if you bring your solutions into class, and we will go through it together and you can mark your answers. Okay? Right, the SUVAT equations, the constant acceleration formula, they can be described in terms of these 5 letters here on the left hand side. So we normally use S for displacement, U is the initial velocity, V is the final velocity, A for acceleration, and T for time. And we can describe this situation here using these letters. So here we have an object at a certain position, and it has an initial velocity u, but it's accelerating, okay, and it's accelerating to the right at a rate of a meters per second squared. After it's travelled s meters, and at time t, it has a velocity v. Okay, so that's the scenario. And what we're going to do, we're going to draw a velocity time graph, and we're going to use that velocity time graph to derive the first 2 constant acceleration formula. Okay, so just bear that scenario in mind. You've got an object travelling with a velocity u that's accelerating until it gets to a velocity v after t seconds and s meters. Okay, so this is what the velocity time graph would actually look like. And we can derive the first 2 SUVAT formula by considering, first of all, the gradient of that line and also the area under the graph. So let's go ahead and do that. So the gradient of the line, well, the gradient is the difference in the y values between these 2 points on the end of the line divided by the difference in the x values, or in this case it would just be the length t. So the gradient, which we know for velocity time graph is the acceleration, is the change in the y values, so v minus u, over the difference in the x values, or in this case it would just be t. Okay, now that is a SUVAT equation, but we don't remember it like that. What we're going to do is to multiply it by t, and we're going to add u to the left hand side there. In fact, I'm going to swap these around, so we have v on the left and we just get v equals u plus at. Okay, and that is the first SUVAT equation that you need to remember. Okay, so that was considering the gradient of the straight line. Let's consider the area now. So the area, let's use the formula for the area of a trapezium. And we know the area is the displacement, which we've called S. So the displacement, the area under the straight line, is half the sum of the parallel sides. So half of u plus v multiplied by the distance between them, which again is our time. Okay, and that is the second SUVAT equation that you need to remember, okay, that you'll be using in the next few examples. Okay, so those two formula, probably useful to just write them down somewhere where you can access them quickly, maybe on a separate sheet of paper so you can have it in front of you when you're answering some problems. Okay, let's do some examples. In example 1, we have a cyclist that's travelling along a straight road and she accelerates at a constant rate from a velocity of 4 meters per second to a velocity of 7.5 meters per second, and that takes her 40 seconds. Let's just start off by sketching that velocity time graph. Okay, so something like that, and let's just label this as velocity time, and then she starts at 4 meters per second and ends at 7.5. Okay, so just put a little dash there to show the end of the velocity and 40 seconds there. Okay, so find the distance she travels in these 40 seconds. Well, the distance, as you know, is the area under the graph. So we just need to use SUVAT for that. And we're going to use S is equal to a half U plus V times T. Okay, so we have the initial velocity, the final velocity, and the time, so we can put them into that formula to work out the distance. So pop in 4, 7.5, and 40 for the time, and that gives us a value of 230 meters. Okay, so that's part A. Let's just label that. Now part B, we need to work out the acceleration during that 40-second period. So let's try the other formula, V equals U plus AT. And we have V, U and T. We just want to work out A, so it's just a case of rearranging this. Okay, just like that. And we're going to have the final velocity minus the initial velocity over that 40-second time period. And that does give you a value of 0.0875. Okay, I'll just put the units underneath. So there you have those two parts of question 1, example 1. Very important to try and draw the problem, because although this is a very simple problem, you will get some problems where you have maybe two different objects traveling at the same time, maybe intersecting each other at some point in time. So it's good to be able to draw the velocity time graphs to get an idea of what is actually going on in the question. But like I said, this one is very straightforward. Example 2. Okay, a little bit more involved, this one. Here we have a particle moves in a straight line from a point A to a point B with constant deceleration, 1.5 meters per second squared. The velocity of the particle at A is 8, the velocity of the particle at B is 2. Find the time taken for the particle to move from A to B. I'm going to get you to see if you can just sketch the velocity time graph for that first part of the question. Okay, it is extended later on, but let's just do the first part and see what we get. So pause the video, do a little sketch of that velocity time graph, and then resume to see if you've got it right. Okay, let's just see if we can draw some axes here. Okay, I'm going to make that quite long. Right, so, and we're going to label our axes. So velocity and time. And just go back to the question. Particle moves in a straight line from A to B with constant deceleration. So if the deceleration is 1.5, that means it's sloping downwards from A to B. At A it's 8, at B it's 2. Okay, so let's just draw that part of the graph, and we're going to do that in blue. Okay, so there we go. There's the first part. So here we have, let's just change to a pen. Here we have point A. Here we have point B. So that's 2 meters per second, and that's 8 meters per second. And the constant deceleration is 1.5. I like to just write that in on the slope. And I'm going to write minus 1.5 because that we work with acceleration in the formula, so I want to make sure I get my signs right. It says the part, sorry, let's go back to the first part again. Find the time taken for the particle to move from A to B. Okay, so we're after this time here. Okay, so let's work it out. So we have, sometimes it's useful just to write down SUVAT. So write down the letters and just indicate what we know. Do we know the distance? No. So I put a little question mark there. Initial velocity, yes, is 8. Final velocity is 2. Acceleration, minus 1.5. And we're after the time. Okay, so we want an equation involving u, v, a, and t. Right, so v equals u plus at springs to mind. And this time we want to rearrange it for t. And just plug in our values. So v, the final velocity, is 2 minus 8 divided by minus 1.5. Okay, and that's going to be minus 6 over minus 1.5, which is 4 seconds. Okay, so here we have 4 seconds. Part B, the distance from A to B, well, that's just the area under this graph here. So area under that blue line. And let's just label that as A. Part B. So we want to use S equals a half U plus V times T. And again, just put our values in. So initial velocity of 8, final velocity of 2, time is 4. We just work that out. And that gives us a distance of 20. Okay, so that's part A and B done. Let's just read the rest of it now. It says, after reaching B, okay, the particle continues to move along the straight line with constant deceleration 1.5. So the deceleration is the same as it is for the first part. Okay, and that's really useful because it means we can treat the whole question all in one go rather than having to try and split it up. So let's just put in the rest of that line. Okay, so we're going to go from here. Oh, that didn't work, did it? Okay, so we're going to put in that line from there and something like that. So the particle is at point C 6 seconds after passing through the point A. I'm just kind of guessing where this is, but it's a pretty good guess, as you'll see in a moment. So here we have 6 seconds. And we're at this point here, which is point C. Okay, so find the velocity of the particle at C. Now, because the deceleration is the same from A to B as it is from B to C, then we can just treat this whole journey in one go if we wanted. Or we could just look at the journey from B to C. It doesn't really matter. So let's do part C over here. So I'm just gonna go from here, I think. So initial velocity is 2. Let's just write down what we know. So displacement we don't know. Initial velocity is 2. That's at point B. Final velocity we don't know. That's what we're trying to find out. The acceleration is the same, that's minus 1.5. And the time is 2 seconds. Okay, so try to work out V. So we're just going to use V equals U plus AT. So that is 2 minus 1.5 times 2. So 2 minus 3 is minus 1. So as you can see, I was right with my graph. It is a negative velocity, and this point here, let's do it in blue so it matches up. This velocity here at point C is minus 1. Okay, so that velocity there is minus 1. So velocity of 0 here at this point, they change direction, she changes direction and heads back to the start. Okay, right. Well, the particle heads back to the start. So part D, find the distance from A to C. Okay, now this is a little bit tricky, but it makes it easier that the deceleration is the same all the way through the question, because we can just do this with one formula. And what's actually happening in this question is particle starts here, and it's travelling with velocity of 8. It's travelling in the positive right direction until we get to this point where it stops, and then it travels backwards. Okay, so travelling back. We want the distance from A to C. Okay, so how far is C from A? Well, we could do this two ways. We could work out the distance underneath this graph. If we knew where this point was, we could work out the area of that triangle. We could then work out the area of this triangle and take one away from the other to get the distance or the displacement. That's actually what they want, is the displacement here. But because the deceleration is the same all the way through the question, we can just do it with one formula. And we do that like this. Okay, we'll do part D over here so we can see the graph. Okay, so S is what we're after. Initial velocity, let's just take it from here. So the initial velocity is 8. Final velocity at C is minus 1. Acceleration is minus 1.5. Okay, so we've written down all the bits that we need to know. All the bits that we know, and we need to know what S is. So let's just rearrange our displacement equation. And we don't even need to rearrange it, do we? So it's just a half the sum of U plus V times T. So 8 minus 1 times 6. Okay, it was 6 seconds. And when we calculate that, so 8 minus 1 is 7. 7 times a half of 6, 7 times 3 is 21. Okay, so there we go. So you can see the journey from A to B, that was 20 meters. She's probably going to travel another maybe 2 or 3 meters and then come backwards. So yeah, another little bit there added on to the 20, and then backwards another bit. So 21 meters from the start. Okay, and in example 3, we have a car that moves from traffic lights along a straight road with constant acceleration, starting from rest at the traffic lights and then entering a speed trap 30 seconds later where it is registered at travelling at 45 kilometers per hour. Okay, let's just draw the velocity time graph to start with. Okay, I'm going to draw some axes first. And essentially this is quite easy, this question. We've just got a car that's travelling from rest until it gets to a certain speed. And we can mark those speeds off as well. So velocity, time. Need to work out this speed here, this final speed. We've been given it in terms of 45 kilometers per hour, but you've probably noticed here a little hint to work in SI units. So we need to convert that. Let's just do that first of all. So 45 kilometers per hour, to work it out in terms of meters per second, we'd have to multiply by 1000, divide by 3600. And we get the value 12.5. So this bit here, that's 12.5. And if we look at the time, that takes 30 seconds to get to there. Okay, so find, first of all, the acceleration of the car. Well, you could use v equals u plus at, but actually it's easier than that because we can just look at the gradient of this line. Okay, so acceleration is the velocity over the time. And that gives you could write it as a fraction. I'm going to write it as a decimal, 0.417 meters per second squared. That's the first part there, that's part A. And then part B, the distance between the traffic lights and the speed trap. Again, you could use the formula for this, but actually all you need to do in this question is to work out the area of a triangle. So distance is half times the base, which is 30, times the height. And that gives us a distance of 187.5 meters. Okay, so just a few simple examples there. Hopefully you've got the idea of these first two SUVAT formula. And here's one for you to try yourselves. Have a go at this question, folks, and do bring your answers into class so we can have a look and we can go through it if necessary. So try this one before you move on. Okay, time for a little bit of practice before we move on to the other formula, folks. Exercise 9C. Do have a go and check your answers with these solutions in the back of the book, and any problems let me know in class. If you do want to challenge, have a go at this question. I think you might find this a little bit more interesting, a little bit more challenging. So again, any problems, bring them to class, and I'll see you there.